In continuing to build up our differentiation rules to include more and more types of functions, we will now consider what happens when we have a function that's multiplied by a constant or a number in the front. Like if we have, instead of just x squared, which we learned how to differentiate using the simple power rule, what if we had 3x squared? How do we handle that? Well, it ends up that it works as nicely as possible. The derivative of a constant, a number, times anything with a variable is the constant times the derivative of the variable part. So, in other words, the derivative d dx of a constant, which I'll use k for, multiplied by some stuff with x in it. I'll use f of x. What this rule says is that this k, this constant, can kind of just come outside of the derivative and we can just keep multiplying by it. We can just find the derivative of the variable part and then multiply that by the k later. Here's a proof as to why this works. If we consider a function c times f of x, which we can use k or c to denote a constant, then when we take the derivative of that function, which this proof is just calling g of x here, we will use the limit definition of the derivative in the proof. When we substitute in g of x plus h minus g of x, that will just be c times f of x plus h minus c times f of x. What ends up happening is that this c here can kind of be factored out of the numerator. That's what happens in this next step. Then the c, this is kind of hand wavy, but there is a rule where when you're finding limits, the constant can come out in the front of the limit. Then what we have here is a constant times the definition of the derivative for f of x. That is just c times f prime of x. So in other words, when we're differentiating a number multiplied by a variable stuff, then we just keep on multiplying by that number, and we can take the derivative of the variable part separately. Graphically, the reason why this is true is because when you multiply a function by a constant, like in this picture, we have twice a function, for example, what that does is it vertically stretches the function. So when thinking of the derivative as giving you the slope of the tangent line at different points, well, these slopes are all going to be doubled. The rises are all going to be doubled if we double the y values everywhere. This would be true if we had a 3 in the front, all of the slopes would be tripled, or a 4, or any constant multiple in front of the function. So when we're finding the derivative, we can just multiply the original function's derivative by the number. This opens up a lot more possibilities of functions that we can now differentiate. For example, let's look at the function f of x equals 3x to the fourth. So before this rule, we were just finding the derivative of things like x to the fourth. But now we have a constant multiple here in front of the x to the fourth of 3. So what this rule says is that your derivative of the entire function is just going to be 3 times the derivative of x to the fourth, which we know how to differentiate. That will be 4x to the third. Now we can simplify this by multiplying the 3 and the 4 together. So that will give us 12x to the third. And that is the derivative of our function using our two rules together, the constant multiple rule and the simple power rule. Please note the difference between a constant function and a constant multiple. A constant multiple is when a constant, a number, is multiplied by something else. A constant function is when there is just a constant by itself with no variables. The derivatives of each of these kinds of things are very different. We know that the derivative of a constant function is equal to 0. But when we have a constant multiple like this 3 here, it stays. It does not become 0. It multiplies by the derivative of whatever the variable part is in the original function. Using the d over dx notation that I used to write this rule would say that if we were finding the derivative of 3x to the fourth, then this constant 3 can come outside of the derivative symbol. So this would be 3 times the derivative of x to the fourth. Then we've isolated just this single x to a single power, and we can differentiate that using the simple power rule. So this becomes 3 times 4x to the third, which is again 12x to the third. You don't have to write both of these things down, but sometimes different notation makes better sense to different people. So I just wanted to show you a couple ways in which you could notate this. We should be able to understand both ways of writing this with the f prime notation and also the d over dx notation. Pause this video and see if you can find the derivative of 4 pi x to the ninth. Here we have a constant in front of some variable stuff. 4 pi is a fancy looking constant, but altogether that's just the number. So when we're finding the derivative of this function, we could write this as y prime, or we can say dy dx. Note the difference with dy dx and d dx. dy dx means derivative of y or y prime. D over dx means take the derivative of what is in the parentheses next to d dx. So the derivative of this whole thing, the 4 pi is a constant multiple that's going to stay and multiply by the derivative of x to the ninth, which we can find using the simple power rule. So it will be 9x to the eighth. Then we can simplify this by multiplying the 4 and the 9 together to give us 36. 36 pi times x to the eighth. And there's the derivative of this function. If we wanted to write this using the other notation, the d dx notation, here's how that would look. D dx derivative of 4 pi x to the ninth. This 4 pi can come outside of the d dx, or outside of the derivative brackets, and we can write this as 4 pi times the derivative of d dx of x to the ninth. Then this 4 pi will multiply by whatever we get when we differentiate x to the ninth, which is 9x to the eighth. And then simplifying again gives us 36 pi x to the eighth. In example 3, we have f of t equals negative 2 t to the sixth divided by 3. Now the way that this is written, it doesn't look like there's a constant times a variable to a power. There is up here, but we've got to handle this 3 in the denominator. So we can always rewrite things like this by kind of extracting out the negative 2 over 3 as its own coefficient in the front. So we can write this as negative 2/3 times t to the sixth. Then that can help us kind of visualize that the actual constant multiple here is negative 2/3, and the variable part is t to the sixth. So when we're finding the derivative of this, f prime of t, that negative 2/3 is going to stay and multiply by the derivative of t to the sixth. That is 6t to the fifth. Then we always want to take at least one step of simplification, and in these cases, we'll just multiply the numbers here together. So negative 2/3 times 6, well, the 3 down in the bottom can cancel with a 3 from the 6 and give us a 2. Then negative 2 times 2 is negative 4. So we will have negative 4 t to the fifth. If you like the other notation, the way that we would write it this way, instead of d dx, we would write d dt, because t is the variable in our function. d dt of negative 2/3 t to the sixth would be equal to negative 2/3, because we can bring this constant outside of the differentiation symbol, times the derivative of, or d dt, of t to the sixth. Then this negative 2/3 just constantly multiplies, and t to the sixth derivative is 6t to the fifth. Then we will simplify this in the same way as we just did to get negative 4t to the fifth. In example 4, we have g of x equals 4 divided by 5x to the 10th. Please note that we cannot just take the derivative of 4, which would be 0, and put it over the derivative of 5x to the 10th, which would be 50x to the 9th. This is not how that works. Please don't make up derivative rules. We can only use the ones that we are told are okay. So what that means is we have to rewrite this function. We will have to do this quite a bit in order to differentiate things. So what we want to do is look at this as x to the negative 10, but we also want to extract the constant and write that as a constant multiple in the front. So the 4 divided by 5 is going to be that constant. So this will be 4 over 5 times x to the negative 10. Now I know that normally we just kind of bring this variable up into the numerator if we are making its exponent negative. That would give us, instead of an x to the 10th down here, 4x to the negative 10 in the numerator. But then we're back in the situation that we just looked at in example 3, where we'll also want to kind of extract out what our constant multiple is in the front. So I just did kind of 2 steps here, looking at this 4 over 5 as a constant multiple fraction, and then also kind of bringing this up, but not to the numerator, but just out of the denominator, and just kind of isolating those 2 things. So here we see that the 4 over 5 is a constant multiple times x to the negative 10. So the derivative of this function, g prime of x, will be 4 over 5, which will stay, times the derivative of x to the negative 10. Well, that will be negative 10x to the negative 11. We want to take at least one step of simplification. We have negative 10 and 5 that we can simplify, so this will end up being negative 2 instead. 4 times negative 2 is negative 8. And then lastly, we want to probably write this as a fraction and get rid of the negative exponent. So this negative 8 has to stay in the numerator. The only thing that can go down into the denominator is the x. And when we do that, we will make its exponent positive. So here's our derivative, negative 8 over x to the 11th. If you like this other notation, this will look like d over dx of 4 over 5 x to the negative 10. And again, this constant multiple can come outside in the front, and we can write that as 4/5 times the derivative of x to the negative 10, or 4 over 5 times negative 10x to the negative 11, which we just simplified to negative 8 over x to the 11th. In example 5, we have y equals negative 1 over 2 radical x. We have to do a couple things here in order to rewrite this in a way where we can find its derivative. First, we've got to get rid of the radical. We can rewrite that as x to the 1/2. Then we have to get rid of that x in the denominator. Well, as it looks, we are kind of in the same situation as we had in the previous example. So we can bring this x to the 1/2 up and multiply it by negative 1 over 2. So this will look like negative 1/2 times x to the negative 1/2. Here we see that the constant that's multiplied is negative 1/2. Then when we find the derivative, which we could write as y prime or dy dx, the negative 1/2 will stay in the front. Then we'll bring down this negative 1/2 and multiply. Negative 1/2 x to the negative 1/2 minus 1, which would give us negative 3/2. We should always take some steps for simplification. Negative 1/2 times negative 1/2 is positive 1/4. And then lastly, we can bring this x down into the denominator and join it with a 4 if we make its exponent positive. So this is 1 over 4x to the positive 3/2. Again, if you like this other notation, you could write this as d dx of negative 1/2 x to the negative 1/2. Then this negative 1/2 can come outside of the differentiation process, and it multiplies by the derivative of x to the negative 1/2. We'll use a simple power rule on x to the negative 1/2 to bring the negative 1/2 down, multiply, and subtract 1 from the exponent, and then do some simplification, which we just saw will lead us to 1 over 4x to the 3/2.